Welcome back, Algebra 2. We are in lesson 115. Oh, we're getting so close to the end of the year. I know y'all are excited. So let's talk a little bit about exponential equations. Fun stuff. So we know that if we say 10 squared, we know that that's 100, right? We know those are equal, that this is an equation, and that's a true statement. So we know that we could say 10 squared is equal to 10x, right? And we know that x would have to be equal to 2, that we could drop the bases and say 2 is equal to x. And then that would still be a true statement, right? Because this would have to be the same thing. So we're going to use this theory and apply it to some more exponent type problems. So let's jump into example 115.1. We'll start there. So here we have 17 set equal to 10 times an exponent, or 10 with an exponent. Now, how can we do this? Well, first we can take this number here and we can put it into a base 10 using our calculator. So let's do that now. We take our calculator, and the way we do that, we're going to clear this out here, and we're going to put in the number 17, and then we're going to turn it into a base 10 by clicking the log 10 button. And that tells us that we're going to use the most significant figures, which is 1.23, because this becomes a 0. When it starts to decline or it goes to a 0, that's the end of our significant figures, and so we're just going to use the first ones. So we can say base 10 to 1.23 is equal to 17. So 1.23 here is equal to 10x plus 2. So now we're going to drop the bases and figure out what x is equal to so that we can solve for x. So we drop the bases and say 1.23 is equal to x plus 2. And when we subtract 2 from both sides, we find that negative 0.77 is equal to x. And so then we can go back and say that 17 equals 10. And if we were to put negative 0.77 in as x plus 2, we would get 1.23. So that is how that works. So we know that those are true statements, right? That's equal. But that is the illustration that we need to understand here. We're putting things into a base 10, and then we're having our exponents be set as equal in order to solve for the missing element. We're going to continue to expound on that in our next example. But first I'm going to talk a little bit about exponential functions and how they work before we apply this. All right, so here we have a graph, and we have two functions shown on this graph. Now, the top function shows starting at the same place as the second function, or the bottom function. We're starting at 200, and it is going up at a faster rate. The curve is sharper, and it's a tighter curve than this one below. So given that information, what would you think, which of these two would be associated with the top function and which would be associated with the bottom function? Now, if you said that you thought the top function was 0.4t because that exponent is bigger than this one, and this one is smaller, it's a smaller rate of increase, so the exponent must be smaller, then you would be correct. That's exactly what's going on here. This function is related to this one. This is an illustration of this function. And this line here is an illustration of that function. And it is directly because the exponent right here is different. This one here is bigger than this one. It has a greater impact. This is the coefficient that goes with time. It has a greater impact on time, and it increases faster exponentially than this one does because of the value of this number. So the way this works is we have the amount of time, the amount at this time, that's AT, is going to be equal to the original amount, that's A of O, times E with a constant times the time. And the constant is going to be the rate at which it either increases or decreases. Now, how would it look for it to decrease? What do you think would be the logical assumption here? Well, if it were, I'm going to change colors. If it were to decrease, let's say the amount of T is equal to 600 E, and let's say it is negative 0.4 T, then that is going to look a little bit like, it's going to start at 600 because that's our original amount, and it is going to go down like this. Okay, but what if we had another one with a smaller rate starting at 600 with the exponent of negative 0.2 T? Well, it would start at 600, but it would decrease more slowly because this is a smaller number, right? So it would look more like this because the rate of decrease would not be as fast, or it would not be as swift. So then this one would be related to this, and this one would be related to this. And it's all directly because of the exponent here, our constant for that particular situation. That's a little bit confusing, I'm sure. Let me take all these little lines off of here. You can see this one, this would be A, and that would be A, and this would be B, and this would be B. That's the illustration I want you to draw the correlation between. And it's all because of this exponent, as I've said numerous times. I'm going to quit repeating myself because you guys are so smart, you can see the difference. When it's negative, the bigger number is going to decline faster than the smaller number. When it's positive, the bigger number is going to increase faster than the smaller number. Pretty straightforward. So let's do some example problems using this theory. All right, so problem number 2. In the beginning, there were 400 bacteria in the dish. The number of bacteria increased exponentially. Now, normally when we've been giving you a problem like this, we would say it would increase by 120% or 400%. Now we're dealing with exponents, and so we're going to use the exponent formulas. And if you don't remember, that's going to be tied to the logarithms that we learned how to use in lesson 113. So if you need a refresher on that, go back to lesson 113 and rewatch that, and that's going to help you solve these. 3 days later, there were 2,000 bacteria in the dish. How many will there be in 8 days? So this is similar to those problems that we had where they were inversely related or directly related. They varied directly, they varied inversely. We have a constant here, and that constant is going to be the rate of growth. So we have to find what that rate of growth, that exponent that represents the rate of growth is for the bacteria, and apply it. We'll do it with the 3 days sample that we're given, and then we'll apply it to the 8 days that we're asked about. So first of all, let's start with our formula. And this is the formula. We have the amount in this time is going to equal the amount that we started with, the original amount, with the exponent of a constant times the time. Okay, so the amount in this time, let me take that off. The amount that we're asking about, the amount in the time, is 2,000. So we have 2,000 bacteria. Okay, and the original amount was 400. So 400 goes in where the AO is. That's the starting point. And now we have E, that's our logarithm E. And we don't know what the constant is, but we do know that it was 3 days, right? So it's K times 3. So now that we have this, we know that this is going to be times this, right? This is times the exponent here, this base. So we can divide both sides by 400 because we know 400 here is a factor. So when we divide, we find that 2,000 divided by 400 is 5. We eliminate the 400 here, and we are left with E. And we're going to just rearrange our factors so that we don't have to write the parenthesis, and just say 3k, e to the 3k. So now we have to find out what 5 is when it is written with this inverse log. So let's pull up our calculator. I'm going to clear that. And I am going to type in 5, and the inverse log on my calculator is e of x. And if you look, it's exactly what this looks like. We have x here, and we have that little e. So we just type in what that would equal, what 5 would equal if it is the power here. And that is, oh, hold on, 5. So that is 148. Is that right? No, that's not right. It's this one. That's the inverse. I'm looking for this one right here. No wonder. So 5, and then you want the logarithm for the value. So that's this. Okay, so that's 1.609. That's the one we want. So we're going to say 1.61 because we're going to round this up. So 1.61 e to the 1.61 is going to be the same as 5. So we write that over here. Now, because of what we did at the very beginning of the lesson, we know we can drop these bases and set these equal to one another. So we drop the bases, and we say 1.61 is equal to 3k. We know how to solve that. We just divide both sides by 3, and we find that k is 0.537. Right? So now we know what our constant is. So now we can write a new equation and apply that rate here in the constant. So now we need to know the A of 8 days, the amount in 8 days. So the original amount was 400. And our exponent now is going to be 0.537 times 8 days. These two will match. So we go ahead and do this math. Let me pull it up. Where's my calculator? There's my calculator. All right, clear this. And I say 0.537 times 8. And I get 4.296, which is going to be the E here. So A of 8 is equal to 400, and the E is 4.296. So now I'm going to use the inverse E, which looks just like that. If I can get my calculator to come back up. Now I'm going to find the inverse of this, and that's what this number is. That's the inverse operation. So I'm going to type in 4.296. What is the inverse of that? And it tells me 73.4055. I'm going to just, because that's a 5, that's really, it's about where you round it, I'm just going to drop it. I'm going to say 73.4. So that would be A of 8 is equal to 400, and this value here is 73.4. All right, so now we multiply that. 400 times 73.4 is 29,360. So the amount of bacteria in 8 days is 29,360 bacteria. Was that 60 or 62? 60. So there you go. That's how you would solve for that. I will say that you'll get a much more accurate result if you just keep it on the calculator. So for instance, 1.61 divided by 3 gives you your constant here. Then you multiply that times 8. You haven't taken anything off the calculator yet. All right, that gives you that constant. Notice it's a little bit different from the number we have here because we didn't round this. We kept it straight. So then when we do the inverse for that, we get a little bit different number. And then we multiply that times 400. We get a little bit different number too. So there is going to be the opportunity for a little bit of fluctuation in the numbers depending on where you round it to. Do you round it to 2 decimal places? Do you round it to 3 decimal places? Are you not rounding at all and just leaving it all on the calculator? So there's going to be some fluctuation there. So I am going to give you some leeway in relationship to what your final number is. But I really need to see your work. If you want to back up your number, if it's kind of far off, I want to see what you've got. So you can always defend your work or your answer by showing me your work and where you rounded and how you rounded if I mark something wrong, okay? And you feel like it should be marked right. So I want to be fair. Show me what you've done and how you got to that number, and then I can give you credit for it if I mark it wrong in the first place. But in the first place, I am going to give you some leeway because I know there's going to be some variation between what my answer book says and what you do, just considering where you decide to round that number to. The main thing I would say is to look for significant numbers. Significant numbers would be, for instance, 1.61 divided by 3. This repeating number here, as a significant number, you would want to just round that up to 7. Okay, and that would completely take care of that. And then that's what our book did as well. All right, so that's just a thought, or just a reminder, I guess. So let's do the next example problem. All right, so here's our problem number 3. In the beginning, there were 4.25 ounces of radioactive material. It decayed exponentially. So there's a clue. It's decaying. It's going away. So that means we're going to have a negative exponent. 10 years later, 3.92 ounces remained. How much would remain after 30 years? So first we have to find our K, our constant, which is our rate of decay. And then we'll apply it to the 30-year mark. So let's begin with restating our formula just so we know what it is. We have A. The amount in this time would start with the original amount times the exponent of K times T. All right. So the amount in that time frame became 3.92 ounces. So 3.92 is equal to the original amount of 4.25. We don't know what the rate of decline is yet, or the rate of decay is, but we will find it. And the time is 10 years. So K times 10 or 10K, whichever way you want to think about it. So we know this is a factor. Oh, I forgot my E, sorry. We know this is a factor. So we can divide this, both sides by that. 4.25, 4.25. All right, we'll pull out our calculator to see what we get. So 3.92 divided by 4.25 is 0.9223529. It's a big old long number, right? So why don't we, let's just look and see here. I'm going to stop it right here because it starts to go up again. You could potentially round that up if you wanted to. I think I'm just going to leave it because 5 is where you start rounding. So I'm just going to, it's kind of an iffy thing for me. I'm going to leave this as the significant figure. So 0 point plus is what my book tells me that they stopped at. So I kind of have a little bit easier time deciding because I can look at the book. So that's going to equal E And I'm just going to rearrange these so it's easier for me to think about them, because that's the way I'm used to thinking about them, is with the coefficient in front of the variable. So now I am going to find the value of this as an e value, right? So let me pull my calculator up again. And I am going to put it back down to this number, 0.9223. And I'm going to do this inverse is the natural logarithm of the displayed value. So this right here. And that's going to be negative 0.08. And because this is a 0, I'm going to stop right there. Okay. When you have a 0, that's an automatic clue that you stop in between here and here. And these will be your significant figures. So that will be e to the negative 0.08. So e to the negative 0.08 is equal to e to the 10 times k. So we can drop these bases and say negative 0.08 is equal to 10 times k. Divide both sides by 10. And we get that it is negative 0.008 is equal to k. And that is our constant. Now we can take this constant and apply it to the 30-year mark. So the amount in 30 years is going to be equal to the original amount, 4.25, with a rate of decay here, k, negative 0.008 times 30 years. Oh, I forgot my e, sorry. So let me go in here and get my calculator. 0.008 negative, you can do that with a little integer button here, times 30 is negative 0.24. Okay, so the amount in 30 years is equal to 4.25 with the log e at negative 0.24. All right, so now I go in and I find the inverse function here of what this is. So I could have just left that up, I guess, 0.24 negative, and I'm going to do the e to the x here. That's my inverse operation. 0.78662786, yada, 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 yada. All right, so I'm going to stop here where the 6 drops to a 2. That's going to be the end of my significant figures. And I am going to use that as my factor to replace e to the negative 0.24. So A, the amount in 30 years, is equal to 4.25 times 0.7866. Now I do that multiplication and I find out the amount in 30 years. There's my calculator. So 0.7866 times 4.25. I have 3.34. The number starts to go down. So I'm going to say 3.34 is my significant figures. So the amount in 30 years that I have is going to be 3.34 ounces. And that is how you would solve that. All right, it's all about knowing how to use the calculator for this stuff right here. If you look, I am just using these two keys here. I use this one first to find out what that E is. And then I use my inverse, once I know what that is, to turn it into a factor. So I use this to go from the whole number or from the decimal number to the E version. And then when I'm in the E version, I use the inverse, the e with the exponent, to take me back here to the whole number. Okay? So that's what you're doing when you solve these. All right, and that is all we have for those types of problems. Now let's talk about compound interest. We did those last year, and they're very similar in relation to this formula. So we're going to go ahead and go back over them one more time so we can refresh our memory. So let me clear this and put one of those on the board. All right, so let's talk about compound interest. So we know how that works. We have the amount and the time, and then we have the original amount, say $100, and then we have the interest plus 1, and then that's going to be times the time. So let's say that I have $100 deposited in a savings account that pays 8% interest. So we have the amount of time, I have $100 in my account, and 1 signifies the original 100%. So the interest amount, if it's 8%, we remember from our pre-algebra days that we write 8% as a decimal by 0.08. So I'm going to add that to the 1, it's going to be 1.08, and then this is my time. So basically what we're doing is we're saying I will have this amount of money, and it's going to start with my $100 times 1.08 for the first year, times 1.08 for the second year, times 1.08 for the third year, and so on and so on and so on, however long that is, whatever that exponent is. It's taking this amount, so 100 times 1.08 is going to be $108, right? 108 times 1.08, that's going to end up being like $116 and some change or something. And then this is multiplied by this, and so forth and so on. And that's how this formula works. We can do the same thing with something called compounding continuously, which means that it's continuously being compounded. It doesn't stop per se. I'm not a financial wizard by any stretch of the imagination, but the formula for that would be very similar. It is A, the amount of time, the amount in this amount of time is equal to the original amount, and actually the original amount is written as principal, so it's written as P, right? So the original amount is P, and that's going to be to the exponent of the rate of growth, and I don't know why that changes like that. I guess I hold it too long. It's going to be the exponent with the rate of growth times the time. So PERT. Your money is PERT, I guess. I don't know. We're going to use this formula to solve a compounding continuously problem. So let's look at these right here. Let me clear this off. And I'm going to scroll down. There it is. All right, so let's look at this problem. Roger deposited $5,000 in an interest-bearing account that paid 7.5% compounded continually. I forgot the ED. How much money will he have in 10 years? Okay, so the amount in time would equal the original amount, the principal, times the exponent of rate times time. So the amount in time, the amount in 10 years would be the principal, 5,000, times the exponent with the rate of 7.5. So we know that 7.5% is actually 2 decimal places over. So that would equal 0.075 because 7% is 0.07, so the 5 comes after. So that's going to be 0.075 times 10. Right? So there's our rate and there's our time. So let's go ahead and figure out 5,000 with that exponent there, and this is just going to shift the decimal place over 1, and that's going to be 0.75. Right, so now we have to figure out what this factor is here, and all we have to do is put in our calculator 0.75, and we pick the one that looks like itself, which would be the E, and that'd be 2.117. I'm going to round that to 2.12 just because that's what the book does. You could leave it as 2.117 because this is a 0. That would be the natural place that I would normally do it. But the book rounds it to 2 because it is a 7 and it's greater than 5, and usually, when it's over 5, it's a no-brainer to round up. So that's what we're going to do. We're going to say the amount in 10 years is going to equal 5,000 times 2.12. And then we do that calculation. 5,000 times 2.12, 10,600. So the amount of money that he would have in 10 years is $10,600. All right, easy peasy. So all we had to do for this one was use the exponent inverse, that IN inverse. There you go. Or the LN, whichever one. It looks like an IN on my calculator, but it's actually LN. That's what you want to use. All right, and that's all we have for lesson 115. I will see you in lesson 116.